Thanks, Vadir.
Yeah, also the information is in the our webpage, right?
Yeah.
Okay. All right, it's my pleasure to introduce today's speaker, Rebecca Willet. Rebecca got her PhD not too long ago from Rice University, and then she was at Duke for quite a few years, and then moved to University of Wisconsin. And in 2018, she moved to the University of Chicago, where she is now professor in the Department of Statistics and Computer Science. Today's lecture is entitled Learning to Solve Inverse Problems in Imaging. Go ahead, Rebecca.
Oh, thank you very much. I'm really excited to be a part of this very exciting seminar series. I listened to Thomas Stromer's talk last week, which I really enjoyed, and very much appreciate the invitation from the organizers. So as Fadil said, I'd like to tell you about some of the recent work I've been doing with my student Davis Gilton and postdoc Greg Ongi on learning to solve inverse problems in imaging. So the basic setup is this. We assume that we observe, instead of an image of interest, some projections or indirect measurements of that image. So specifically, we could represent an image as a list of pixel values, beta, and have a matrix or operator X that describes how those pixel values get mapped to an observation Y, which would correspond to X beta plus some noise epsilon. And so when we talk about inverse problems in imaging, our goal is to recover this image beta from Y. So this is a pretty generic problem statement that arises in a wide variety of different problem settings. Examples include things like in-painting, deblurring, super resolution, compressed sensing, MRI or CT reconstruction, radar imaging, and many more. And so the question really is how we can develop better strategies for recovering data from Y, especially when this matrix X is ill-conditioned and so that the overall inverse problem is ill-posed. So as many of you know, classical approaches stem from perhaps a least squares approach, where we would say, well, I've got this linear system of equations, so let me try to find the least squares solution. And we can look at that approach in the context of deblurring. So what I have here, actually, can you guys see my pointer? Hopefully. What I have in the upper left is a blurry image, and this version has no noise whatsoever. And now if I try to use the least square solution, then I get a perfect reconstruction. It looks outstanding. But if I were to take that blurry image and just add a tiny amount of noise to it, so small that it's imperceptible to the eye, even that tiny amount of noise can cause significant problems in the least square solution, causing these huge errors and huge pixel values. And so the goal of regularization is to avoid this oversensitivity to noise. So the problem with least squares is that we have to invert this matrix X transpose X. And so when X has got some very small singular values, this inversion is very ill-conditioned, and we get this huge blow up of any small noise elements that are inside Y. And so what we might do instead is say, well, let's try to minimize not only the sum of squared errors, but an additional term that essentially penalizes the sum of the squares of all the pixel values in beta. And we can actually write the solution to this optimization problem in closed form. And what we see is something that looks a lot like least squares. But instead of inverting X transpose X, we invert X transpose X plus lambda identity. And so even when this tuning parameter lambda is very small, we have a much better conditioned matrix to invert. And so we no longer have this huge blow up of noise terms. And so here's an example of this in action when we apply it to the noisy image. And we see it's obviously not perfect, but it's far better than the least square solution. So from this sort of starting point, people have spent decades thinking about other ways in which we might suppress noise or exploit structure within images to get better reconstructions. And have considered this general framework of image regularization. So examples that you might be familiar with would include, for instance, total variation, where we would take an image and look at its first and second order, first order pixel differences, either vertically or horizontally, and add the absolute values of those up. Or we might look at the sparsity of an image in a wavelet basis, or even look at things like different patches in an image and try to create regularizers or models that exploit the fact that there's a lot of redundancy or self-similarity among those patches that can be leveraged to remove noise. So all of these approaches can be used, or all of these models can be used to help us improve the way that we solve inverse problems in imaging. But all of these approaches are things that are based on our understanding of the geometry and structure of images. So it's an observation, and it's based on a wealth of experience and intuition, but less data-driven. So what I'd like to talk about today are ways in which we can actually figure out models or regularizers from training data as opposed to from geometric models. So throughout, we're going to consider this generic framework where we're going to take an observation vector y and try to recover an image beta by minimizing y minus x beta sum of squared errors plus some regularization term to get out an estimate beta hat. So this regularization term could be Tikhonov regularization, total variation, etc. Or it could be something that we try to learn from training data. And the question is, how do we actually go about this? How do we use training data to find a good regularizer? In the last several years, there's been quite a bit of work done on this problem. And rather than go through all of the different approaches that have been proposed, what I'd instead like to do is to suggest a particular taxonomy or a collection of different categories of approaches that I think are particularly relevant and representative. So those categories include, first of all, model agnostic approaches, where we have a bunch of XY pairs, so images, beta Y pairs, so images and observation vectors. And we want to learn how to do the solve the inverse problem, but we don't explicitly incorporate knowledge of this forward model X. And we'll look at an example of that. Then we'll also look at decoupled approaches where we separate out the process of learning and the process of solving the inverse problem. And the idea is we just try to learn the geometry of images and then just plug it into some reconstruction approach. We'll then look at unrolled optimization methods and a new approach that my team developed called Neumann networks. And we'll explore some of the trade-offs among these different methods as we go. So first, let's consider this model agnostic framework. And this is, I think, especially effective in applications like super resolution, where we have some often a very coarse idea of what this forward model X is, even if we don't have a precise model. And so in this setting, what we might do is take our raw data, a low resolution image, and then try to upsample it to the desired resolution. And we can think about that as being a very coarse, approximate inverse of our forward model. So it's in no way, representative of, say, the pseudo inverse of the true X, but it's just sort of capturing the fact that we want to get up to a certain resolution. And then what we might do is we might train a machine learning system like a deep convolutional neural network to map this approximate high resolution image to a high resolution, high quality reconstruction that does not exhibit the blurring or blocky artifacts that we might have had from this very coarse initial inversion, in this case corresponding to bicubic interpolation. So this is an approach that's received a fair amount of attention in the literature, particularly in the context of super resolution and deblurring, where the forward model under consideration is something that's relatively benign. The challenge with this approach is that because we don't incorporate any knowledge of X into the entire reconstruction process, we generally need lots of data to train this system, because it requires us to essentially learn features of the forward model X. So we're essentially learning everything that we might need to know about X to produce a good reconstruction from our training data. Okay, so now we can contrast that with a decoupled approach, where, as I said before, we first do all of our learning and leveraging of our training data, but then we've got a second phase where we explicitly account for our forward model X. So I'm going to show you a couple of different examples of this general approach. And the first one starts as follows. It says, remember that our general framework is going to be to think of our estimate as a solution of an optimization problem where we minimize the sum of squared errors plus some regularization term beta. So what we might do is imagine that we know what this regularizer R of beta is and think about how we would solve that optimization problem. And one approach that we might consider, for instance, would be a proximal gradient algorithm. So in this case, what we would do is we would start with some initial estimate of beta hat 1, and some step size. And then we would iterate, alternating between two different steps. The first step is essentially a gradient descent step on the squared error or data fit term. So we take our current estimate, beta hat k, and then take a step in the direction of the negative gradient of our squared error loss. Or in other words, we push our estimate a little bit closer to fitting the data. And then in the second step, we would use our regularizer, where we essentially take this intermediate estimate, zk, and try to push it towards something that has a better value of this regularization term. And we can think about this second step as essentially a denoising step, where we're essentially trying to take zk and remove noise from it using this regularizer R. And we could then think about trying to start from this framework and employ learning by saying, first, let's try to learn a neural network that can perform denoising. So instead of explicitly trying to learn this R of beta, we're just trying to learn this denoising step. We're trying to learn a mapping from noisy ZKs to denoised betas. And then once we've learned this, then we can plug it in to this proximal gradient algorithm so that overall our method has a learned component and a component that depends on our forward model X. But again, I want to emphasize that I call this method decoupled because we learn this denoiser at the beginning without taking into account at all what this forward model X is. And it's only after the entire learning process is done that we fix this denoising step, or we fix our regularizer R, and then we just plug it in to the proximal gradient algorithm and we solve the inverse problem. Okay, so this is one example of a decoupled approach. Another example uses generative adversarial networks or generative models. And the idea here is this. Imagine that all of the images that we want to reconstruct or that we care about lie on some low dimensional submanifold. If we knew what that manifold was, then we could use that to form a regularizer. So we could say, for instance, that our regularization term, R of beta, is 0 for any image beta that's on this manifold and infinity otherwise. So if we set up our regularization function like that, then essentially what we'd be doing is we'd be searching over all images on this manifold for the one that it best fits our data. Okay, so that would be what we might do if we knew what the image manifold is, but of course we don't. And that's where machine learning and generative models come into play. So in particular, what we could do is we could say, let's learn a generator G, where the output of this generative model is an image beta. So we can input different input variables Z that are in a lower dimensional space that reflects the lower dimensionality of this manifold. And the output of G is going to be some image on this manifold. So once we have that generator G, we could define a regularizer that says, let's have 0 cost or penalty for any image that could be produced by this generator that's in the range of the generator, and 0 otherwise. So once we've taken all of our training data and learned this generative model G, and there's a wealth of literature on how to learn these generative models, Then we can fix G and devote our attention to solving the inverse problem. So in particular, all we would do is we would choose the image beta that's in the range of the generator that best fits the data. Or we could think about it as trying to optimize over all possible inputs to the generative model that produces an image that best fits our data. Okay, so this is a very interesting idea. It's received a lot of attention in the literature, and there have been a lot of different variants of this approach proposed. As I said before, it is an example of a decoupled approach because, again, in the first stage, we use our training data to learn this generator G. And the way we learn the generator G is completely independent of whether we're aiming towards an MRI problem or an in-painting problem or anything else. And then once G is learned, then we step aside and say, okay, now we want to solve a particular inverse problem, and I'm just going to plug G into some solver for that inverse problem. Okay, so here's an example of this approach in action for an in-painting problem. So there's an original image of this woman's face. Our observation is missing a bunch of pixels in the middle of her face. And if we were to train a generative model with 80,000 different images of faces that are all nicely centered and registered, et cetera, and then use this generative model reconstruction framework, then we get a pretty good looking estimate. But if I were to reduce the number of training samples down to 2,000, this method completely falls apart. And I don't want to come across as if I'm picking on this one particular approach because every decoupled method that our team has tried exhibits this sort of phenomenon where if we have a relatively small number of training samples, it can really just crash and burn and perform very, very poorly. And so the question really is, why is this occurring? And I think it's an important question because if we were interested in things like reconstructing images of cats, then maybe we don't care so much because there are millions of images of cats available to train on. But there are many applications, for instance, some of the medical imaging applications that I mentioned, where we have many fewer samples, many fewer training samples, and we really need to be able to use them as well as possible or get the maximum accuracy given that number of training samples. Okay, so let's try to dive into why these decoupled methods have this poor performance when we have a relatively small number of training samples. The way I think about these approaches is generally working is that when we do the training phase, what we're doing is we are essentially learning a probability distribution over the space of all of the images that we might want to reconstruct. And once we have that distribution, that prior, then we can use that prior knowledge of image geometry and structure to solve our inverse problem. And so in the decoupled approaches where the learning is the learning of the prior. But if we take this in-painting example, if we think carefully about this in-painting example, essentially what we're doing is we're learning this prior overall images. And you could argue that that's really overkill for the in-painting task. So in particular, my goal here is to fill in the middle pixels in this woman's face. And there's a lot of pixels in the image that are totally irrelevant to this task. So the fact, for instance, that the background is blue and has some letters in it doesn't tell me anything about how to fill in those pixels in her face. And yet, when I use these decoupled approaches and I try to learn this full probability density, I'm having to use my training samples to learn all kinds of structure in the image that's irrelevant to this in-painting task. So what I would argue is that instead, we should be focused on conditional density estimation, at least implicitly. That instead of trying to learn distribution over all possible images, what we really need to understand is the distribution of, in this case, the missing pixels conditioned on the observed pixels. Or more generally, we want to understand the distribution of all of the images in the orthogonal subspace of our measurements, given our measurements. And there is good reason to think that this might be able to help us with these issues of dealing with small numbers of training samples. So there's a wealth of literature and statistics on density estimation and conditional density estimation that describes how many different samples we need to achieve a target level of accuracy in estimating the density or conditional density. And in particular, in many cases, the conditional density can be lower dimensional or smoother than the full joint density. And so learning it can require dramatically fewer samples. We can also see that conditional density estimation seems like a reasonable sort of framework to think about this from a different perspective. So in particular, imagine that we wanted to find the mapping from measurements x beta to an estimate beta that's as accurate as possible on average. So rho is going to be essentially our reconstruction algorithm that maps our measurements to an estimate. And we want to make sure that we minimize the mean squared error of our estimate. So we want to choose the very best rho. And we're going to call that best rho rho star. So this hopefully is what we're going to be learning as we go here. So one of the things that we can show is the form that this rho star will take. Under some conditions, in particular, if we assume that this forward model X is full rank, then we can write the mean squared optimal reconstruction function rho star as having two different terms. The first term here is the pseudo inverse of X times our measurements Y. And that's going to get multiplied times the orthogonal subspace of X transpose times a conditional expectation. So in red here in this box, I've got a factor that is something that I don't know, that I'm ultimately going to have to learn from data. Everything else in this expression is something that I know. And what I have to learn from data is related to a conditional distribution. The distribution of the stuff that I don't know in the context of in-painting, the missing pixels given the observed pixels. And so from this perspective as well, we see that this notion of this conditional distribution is sort of essential to having optimal estimators. Okay, so what this suggests, if we put all these ideas together, is that because estimating conditional densities can require far fewer samples than estimating the full density, and because the conditional density shows up in the optimal reconstruction expression, then whenever we know our forward model X a priori, we should be using it throughout the learning process. That somehow if we're ignoring X while we're doing learning, that we must be doing something that's suboptimal or that is sort of an overkill step that perhaps is unnecessary. So with that in mind, what I'd like to discuss now is the third category of approaches that we consider, which are unrolled optimization methods. And these are methods that do incorporate this forward model X at every stage of the learning process. So in particular, let's again just imagine that we knew our regularization function R of beta and think about how we might use that in order to come up with a reconstruction. So as we said before, our estimate beta hat corresponds to minimizing the sum of squared errors plus this regularizer R of beta. So imagine that then we wanted to solve this optimization problem by just using gradient descent when our regularizer is differentiable. So we start with some initial estimate and then a step size eta. And then at every stage, our new estimate is going to be our old estimate plus a step in the negative gradient of our squared error plus a step in the negative gradient of our regularizer. And I've illustrated this in the bottom using a block diagram where I do this for B different iterations. So I start with some initial estimate, and then in each block, I can see I've got my step that corresponds to the negative gradient in the direction of my squared error loss, and in parallel, a step that corresponds to the negative gradient of my regularizer. And I do this B different times. So with unrolled optimization then, the key idea is to essentially replace the gradient of my regularizer here with a learned neural network. So within my block diagram, I've got a learned neural network in each one of these bottom branches. So this has some kind of parallels and similar structures to what we saw when we looked at these proximal gradient methods a few slides ago. But the key feature here is that this approach is trained from end to end. So in other words, when we try to choose the weights of the neural network, what we're doing is we're trying to ensure that the output of this entire process from start to finish, beta hat after B blocks, is as close as possible to the true beta. And so when we measure that performance, well, beta hat now is a function of these weights and of the forward model X. And so as we try to update the weights, every time we update the weights, we're explicitly taking X into account as we perform these updates. So this is an example of a method that, unlike the decoupled or agnostic methods, is exploiting knowledge of X at every step of the training process. Okay, so we're going to come back to this unrolled optimization approach in a couple of minutes. But first, I want to also show an alternative framework of Neumann networks. So again, what we're going to do is assume that our regularizer, R of beta, is a differentiable function. And we write out our estimate as corresponding to the minimum of the squared error plus our regularizer. So in this case, we can actually write out what this solution might be in closed form using an operator corresponding to the gradient of the regularizer. Now in this, we've got this noisy kind of, or I'm sorry, this messy sort of inverse term. And now what I'm going to do is I'm going to take this inverse operator and approximate it using a Neumann series. And now what I can do is I can, like I did with gradient descent, take this expression for an estimate and write it using a block diagram. So again, I've got B different blocks, just like before. Within each block, I've got two parallel branches, one branch that uses my forward model X, and another branch that accounts for my regularizer gradient, grad R. And as before, once I have this block diagram, what I can do is I can replace the gradient of the regularizer with a learned neural network. So now what I'd like to do is return to the gradient descent network and actually compare and contrast these two different approaches. So what I'm showing here now are the gradient descent network and the Neumann network side by side. And we can see that they have some features in common, which are positive. In particular, they have the upper blocks incorporating knowledge of the forward model X, and the lower blocks being components that we can learn and corresponding to the gradient of the regularizer. The key difference is that the final output of the gradient descent network is something that's been through every single block of the process, of the diagram. And in contrast with this Neumann network, what we're doing is we're computing our final estimate by cleaving off the output of every single block in the series and adding them together. With this framework, if I were to have a small change in this first block, then it's going to have sort of an immediate effect on this final output that might be more somehow muted if it has to go through all of the different blocks in serial within the gradient descent network. Okay, so let's just think about this Neumann network framework in a little bit more detail. So we've got a lot of different empirical examples that I'll show you in a few minutes. But first, I just want to dive into a little bit more of where this Neumann network, some of the features of this Neumann network. So first of all, let's return to the idea that we talked about a few slides ago on the optimal reconstructor, rho star. So remember, rho star was a mapping from some measurements y to the optimal estimate beta hat. And what we wrote before is that it had two terms, the pseudo inverse of x times y plus x perp transpose times this conditional expectation. And we can actually rewrite this in a way that's going to be helpful in a second by expanding this pseudo-inverse term using a Neumann series. Now what we can do in parallel is we can say, with that Neumann network architecture that I just proposed, what is the form of the output of that network? And the output of that network is going to essentially correspond to two terms. The first term is going to look like a truncated Neumann series of the pseudo-inverse. So we can compare the things in the two green boxes and see that one is just a truncated sum or a truncated version of the other, but they have the exact same overall form. And then we can look at the second terms and we can see where the optimal MMSE reconstructor corresponds to this conditional expectation. What we're going to show or have in our Neumann network is in its place all of the different terms that are learned through our training process. And so one thing that you can conclude about this Neumann network form is that essentially what we're doing by the way it's constructed and architected is implicitly learning this conditional expectation that we said was essential to good sample complexities and good performance. Now, you might argue with me here that this whole premise of starting with the Neumann series is not a good one, because the Neumann series holds for linear operators. So in particular, the Neumann series says that if A is a linear operator, then the identity minus A inverse can be written as this infinite series. But in our case, A, this general A would correspond to the identity minus eta times x transpose x, but minus eta times the gradient of R. So now if we're going to have the gradient of R correspond to a learned neural network, then all of a sudden the gradient of R is no longer a linear operator, which means A is no longer a linear operator, which means this Neumann series expansion no longer holds. And so you might ask whether using this Neumann series as a foundation for building one of these inverse problem reconstruction methods makes any sense at all. So to try to understand why this seems to be effective in practice and a reasonable approach, we're going to consider a case study where we imagine that all of the images we want to reconstruct belong to a union of low-dimensional subspaces. So this is a model that's been widely used in image processing and computational imaging, with one famous example corresponding to the Yale B data set and showing how the images in that data set lie in a union of subspaces. So again, we're not going to exploit this model in the way that we train or construct our Neumann network. The network is exactly as I described before. But what we're going to do is we're going to say, if somehow all of our training data were to lie in a union of subspaces, then what would the Neumann network do in that case? So what we were able to show in this case, where the training images, the betas, all lie in a union of subspaces under some reasonable assumptions on X, is the following. First of all, we could imagine that if we knew what that union of subspaces was, then we could write down what the optimal regularizer or optimal regularizer gradient might look like. And unsurprisingly, it's piecewise linear in beta. So for all of the images beta in subspace 1, the optimal regularizer is some linear function of beta. And for all of the images beta in some other subspace K, the optimal regularizer gradient is a different linear function of beta. So the regularizer gradient that we're searching for and trying to represent with our Neumann network needs to, well, the optimal regularizer gradient should be piecewise linear. And if we were to build a Neumann network with ReLU activations, we're going to be able to closely approximate this piecewise linear structure. In addition, if we were to consider all the different blocks within this Neumann network, for a given input, the outputs of all of those blocks are going to belong to the same subspace S sub k. So for a fixed input, the gradient of the regularizer is essentially behaving like a linear function. So if we were to consider all possible inputs to this Neumann network, then the gradient of R is no longer linear. But if we were to only consider inputs coming from one subspace, then the outputs of all the blocks belong to that same subspace. And so the gradient of the regularizer behaves like a linear operator, in which case this Neumann series foundation that we built upon is a completely justifiable and reasonable model. Okay, so just to kind of sum up, the key ramifications of the theory are that, first of all, the learned thing, the thing that we learned, the gradient of the regularizer, is going to reflect the union of subspaces structure that underlies our training data, even though we don't somehow use some prior knowledge of the union of subspace geometry when we're constructing the network architecture or when we're doing training. In addition, for a fixed input, the outputs of all the blocks are in the same subspace. And finally, the gradient of the regularizer is only going to affect our image beta in the null space of our forward model X. Okay, so those are the three claims that arise from this theoretical investigation. And this is something that we can empirically verify in some toy settings. So in particular, one of the things that we did is we generated some small scale data that belonged to a union of subspaces. And we modeled a setting where our observations corresponded to only measuring the first 5 samples and the second 5 samples being missing. And then what we did is we looked at, as we trained a Neumann network, we looked at the outputs of all the individual blocks within the network, and we empirically verified that all the blocks lie in the same subspace. We also we looked at this condition, or I'm sorry, this ramification of the theory, that the regularizer gradient was only affecting the image in the null space of X. And we again see that empirically. We see that the first 5 samples are never affected by our learned regularizer, and these 5 samples do correspond to the null space of X. And our final theoretical claim was that the gradient of the regularizer was going to reflect this union of subspaces structure. And so we can verify this empirically by looking at 2 images, beta 1 and beta 2. And we can see whether our learned regularizer gradient is behaving like a linear operator or not when beta 1 and beta 2 are both from subspace 1, both from subspace 2, both from subspace 3, or where they're from 2 different subspaces, or when they're just random quantities. And what we can see is that when they're both from the same subspace, then this thing that we're learning behaves linearly, and otherwise it's behaving non-linearly, which is exactly what our theory predicted. Okay, so to wrap up, I just want to show a few empirical examples. And one of the things that I'm going to show in the empirical results is not only the results of the Neumann network, which we've discussed a little bit now, but also a preconditioned version of the Neumann network, where instead of having an input that's simply X transpose Y, we could instead do a simple reconstruction like a Tikhonov regularized reconstruction that we talked about way at the beginning, and then modify the internal blocks of the Neumann network to account for the fact that we've got this preconditioned input. And this can yield some nice empirical advantages. Okay, so we had these 4 different classes of methods, and for the experimental results, I've chosen one representative approach from each of these 4 different classes to consider. So for the agnostic methods, we're going to look at a residual autoencoder where the input is X transpose Y. So it gets a tiny bit of knowledge of X just for the input to the network, but then learns how to correct for that initial estimate. We've got this approach that is decoupled using a generative model that we talked about before, unrolled gradient descent, and Neumann networks. Okay, so here are the results, just anecdotal results for two different numbers of training samples. So first we look at the performance when we have 2,000 training samples, and then we look at the performance when we have 30,000 training samples. What I'm showing on the top row is the ground truth and the 4 different reconstructions for the 4 different methods. And on the bottom, I'm showing the input to each one of these networks, X transpose Y, and the residual images. So the residuals, the blacker it is, the better. It's basically showing you how big the errors are and where they're concentrated. And these have been amplified for visibility. And so what we can see is that for all sample sizes, the Neumann networks are giving fewer artifacts and smaller errors, but that this is especially clear when we have small numbers of samples, which was our target from the beginning. And that methods, especially like the agnostic and decoupled methods that don't account for the forward model X during the training, really suffer when we have small numbers of training samples. And this is not just true, of course, in this one toy example of an airplane, but really across the board. So we considered many different training sets, Celeb A, CFAR, STL10, and we considered problems like compressed sensing, in-painting, super resolution, deblurring. And across the board, what we see is that Neumann networks and the preconditioned Neumann networks consistently give higher PSNRs than these alternative approaches that we've discussed today. One of the kind of key target application areas of this whole line of work is in applications like medical imaging. And so here I'm actually showing the results of some different approaches in the context of MRI reconstruction. So here's the original image, and below it, I'm showing the mask of the values of the in K space or in Fourier space where we collect measurements. And then I've got reconstructions for the preconditioned Neumann network, the Neumann network, the current state of the art for MR reconstruction using machine learning, modal, and then finally classical total variation denoising. And what we can see in this example is that all of these methods are doing well in terms of PSNR. The learned methods have a slight advantage here. But I think the key thing to note is that the total variation reconstruction took 350 seconds, whereas these learned methods are able to achieve higher quality results with dramatically less computation time. But as we start to think about medical imaging applications, we need to start thinking about goals beyond PSNR values. And so we, in particular, need to thinking about some of the key trade-offs that arise when we consider using machine learning in inverse problems in imaging. So the first one is one that we've talked about quite a bit already, generality versus sample complexity. So what we've seen is that if we know X, then we should be using it during training, and that can reduce the number of samples that we need to achieve a target level of accuracy. Of course, the problem with this approach is that it is less general. So every time I've got a new inverse problem that I want to solve, it means I've got a new X, which means I have to restart my training process. So having these methods that leverage X from the get-go are going to generally require retraining for each new problem. Another trade-off, and I'm going to show some examples of this in just a second, is reconstruction accuracy versus sensitivity to model mismatch. So in particular, you could imagine, for instance, trying to learn how to reconstruct MRI images for one scanner, and then trying to use that for a different scanner, which has maybe been calibrated slightly differently. So it has a forward model that we might call X prime, which is slightly different than X. We also have trade-offs related to reconstruction speed versus guarantees. So some of the methods like Neumann networks are trained to be fast. We constrain the number of different blocks B to be small from the outset. And that can be much faster than methods that require us to plug a learned component into an iterative solver, which might have to run for hundreds of iterations. That said, when we fix the computation budget a priori, it can be very difficult to characterize the effect of that on learning accuracy and performance. And then finally, in distribution versus out of distribution performance. So when we think about problems like medical imaging, you could imagine that ultimately we'll be imaging people with tumors or lesions that have a geometry or a shape that was never represented in any of our training data. And we ultimately want to make sure that we're going to be able to reconstruct that geometry in those images accurately. Okay, so I have just a couple of anecdotal examples of some of these trade-offs. One is robustness to forward model change. So in the top row here, I'm showing 3 different methods where I train with one forward model, and then I also use that forward model at test time. So exactly the kind of framework we've been considering all along here. But in the bottom row, I'm training with one forward model, X0, and test with another forward model, X1. So this would correspond, for instance, to moving over to a slightly different scanner at test time. And we can see that this results in a drop in the PSNR and the reconstruction quality, which is what we would expect. But I would argue that this is still an interesting and wide open area of research because we don't have a good sense of how different training regimens or how different neural network architectures affect how big or how small this drop might be. We also are interested in how well we can reconstruct features that are not in the training data. So in this example, what I've done is when I say what I mean is my student Davis, trained these different networks to reconstruct these MRI images. And then we created a test image shown here and then zoomed in below, where we introduced a small artifact, or I guess a square-shaped tumor that was not present in any of the training data. And we wanted to see how well we could reconstruct it. And so here we can see the reconstruction corresponding to Neumann network or unrolled gradient descent or a residual or a resonant. In all cases, we are able to reconstruct that feature, but we definitely have some strange ringing artifacts on either side of it. One of the reasons that I think that this is challenging is that, of course, it's impossible to represent every possible kind of geometry or of every possible tumor or lesion in these giant MRI images. But one of the mechanisms that I think that we might be able to use to somehow mitigate this challenge is to shift from trying to model the geometry of the entire image to instead thinking about taking images and dividing them into blocks and then modeling the geometry of those blocks or patches. So in particular, we can think about our regularization block. Instead of just being a giant neural network, we could think about it as corresponding to taking an image, breaking it up into patches, subtracting the means from all those patches, then having a neural network that maps it to denoised patches that we can add the means back into, and then recombining the patches. So what this means is that the learning now requires us to learn the structure of these patches, which of course lie in a much lower dimensional space, and we've got many more examples of patches, which suggests that we might be able to learn it much better. And we can see this in practice, where we looked at a Neumann network with either 100 or 500 or 1,000 training images. And I'll just highlight a few different data points in here where we're looking at peak SNRs. So if I were to try to learn the geometry of 64 by 64 patches using 100 images, then my PSNR is about 29. Now, if I wanted to improve that, there are 2 different things that I could do that work about equally well. One is I could just increase the number of training samples by an order of magnitude. This could be a pretty expensive proposition and pretty difficult to implement in practice. But alternatively, I can just keep that 100 images that I already have, but instead of modeling 64 by 64 images, model 8 by 8 images. And that also gives me the same amount of increase in the PSNR. So in other words, with the Neumann network, shrinking the patch size from 64 to 64 to 8 by 8 has a comparable effect as a 10x increase in training size. And I hypothesize that in addition to having this nice effect in PSNR, patchwise regularization is also going to give us increased robustness to things like oddly shaped tumors that we haven't seen before within these large MRI images. Okay, so to conclude, we've spent a lot of time today talking about this Neumann network structure and other methods like the gradient descent network and how they can incorporate knowledge of the forward model X in order to yield good reconstructions of images. I think one kind of high level way to think about some of these approaches is that the entire block diagram, like I've illustrated here, can be thought of as one giant neural network, where some of the edges in the neural network, as I've shown in my little colorful illustrations here, are things that I actually have to learn and set using stochastic gradient descent and backpropagation to try to minimize my loss. And other edges in this neural network, I am holding fixed. I am not learning. And instead, I'm allowing the physics of my observation model, my forward model X, to dictate the weights of those edges. And so what this suggests is that we're essentially using a physical model to constrain the parameters of a neural network. And that by doing that, we're able to achieve much lower sample complexities and much higher accuracies. And I think this is a pretty interesting concept and begs the question of whether we can more generally characterize connections between neural network architectures and physical models and use that insight to help us design better ways of constructing neural network architectures. So thank you very much for your attention. We do have a paper on this on arXiv, and then there have been a couple of follow-on conference papers that go into some of the nuances of things like patch-based regularization or some of the theory of the MMSE estimators. And with that, I'd be more than happy to answer any questions.
Thank you so much, Rebecca. I'm the only one that can applaud. Are there questions from the audience? If you have a question, please raise your hand and then I can unmute you. Anybody?
I know it's a big group and people might be feeling shy, but I'm happy to also, if people have follow-up questions via email, I'm more than happy to respond to emails. Or if people want to ask questions in the little Zoom chat window, that's also totally fine.
There's a bunch of comments about your talk, but I don't see any questions.
I mean, I might have a question or more remark, I guess. So, Becca, you spoke a lot about integrating the forward operator into the training of the regularizer by inserting this into the network. But there is also actually in some of the broad classes of learning approaches to inverse problems that you mentioned, there are also ideas to integrate the forward operator into learning the regularization by using it to create a training set. Because if you, for instance, if you would have a nice linear forward operator with a pseudo inverse, if you would use that to create training examples, for instance, maybe going back to your picture of this generative idea of lying on the image manifold and lying outside of the image manifold, one thing that you could do to integrate this forward operator into that is to say a bad image is an image that results from applying the pseudo inverse to the data. And so there are ideas around that. And also, if you think about this class of approaches that are called, or that some people call post-processing, learned post-processing, where you first invert and then you use a neural network to regularize. Also here, indirectly, the forward operator is used because you're starting with an image that has the typical artifacts from that are coming from the pseudo-inverse of your operator.
Yeah, so these are great points. I mean, regarding the first one, if we wanted to think about this, the question is, well, what exactly can we or can't we assume we have here? And different papers have considered different things. So some, like the super resolution reference that I have here, they're just doing bicubic interpolation. So it's an extremely coarse representation of the somehow inverse of the downsampling process. And so now my network here has to do a lot of heavy lifting because it has to somehow learn everything that was not captured by this bicubic interpolation of the downsampling process. But there are other papers that and in fact, our own experiments, just to try to really be as fair as we could, just had this initial estimate computed as X transpose Y, where we used the actual X. So we gave these methods sort of a little added boost above and beyond what a lot of that literature does. And so, there are some problems like deblurring and super resolution where that's okay. And there are other problems where we've found that it works much, much more poorly. And it seems to depend a lot on what the conditioning is of that forward model. And it's not something that I've got a really clear understanding of exactly what those trade-offs are. All I would say, though, is that sort of our whole history in terms of computational imaging, for the most part, does not say, let me just come up with an initial, estimate via the adjoint and then apply regularization. But there kind of always is this more back and forth. And so I don't see a compelling reason to think that all of that acquired experience is irrelevant here and that this would be the right approach. But that said, that's a very hand-wavy way to think about things. Then the first thing you said was related to this notion of the manifold, where you said maybe what we could do is we could say the bad images off the manifold correspond, or I'm sorry, you wanted to say X transpose Y would be off the manifold.
So I'm not directly speaking about how you are using this here later on in this deep image prior sense, but you could, one way of teaching a regularizer that is more bespoke to the type of inverse problem you're solving, to penalize or not penalize reconstructions, is to create, to say what is off the manifold are, for instance, when you think about CT, when you apply the filtered back projection to your measurements, then you see this typical, well, depending on your measurement process, you might see some typical artifacts,
Yeah.
So that was that, and so what I wanted to say is there are ways how people train regularizers that are actually taking the forward operator into account.
Yeah, that's very interesting. It's a little reminiscent, I think, of some of the other things in statistical learning theory where we would somehow use data dependent regularizers. I wonder if there might be a connection there that would be interesting to explore. That's a great idea.
Yeah, we can discuss offline.
Are there other questions from the audience? I just maybe one quick remark, Rebecca. You talked about the need to have some learning regularizer from small data sets. In your vision, how small is small going to be, in practice?
Yeah, that's a great question. So for instance, I mentioned in MRI, the current state of the art is this method modal, MODL, and they have a data set that goes along with their paper and their method. And that data set, I think, had 10 images in it. I mean, these were 10 multi-slice images. And so you can expand these 10 different, the data from these 10 different people into a larger collection of images. But I wouldn't say that those are independent images because they're just coming from 10 people. Now, there have been other works where people have collected larger collections of images for, say, fast MR, which is sort of just focused on the knee, for instance. And so there you might have hundreds, but or maybe thousands, but it gets tricky. And I guess ultimately, it depends on what you need. So if you are going to need separate data sets for every new scanner, then assuming that you're going to have a training set that has thousands of images might not be realistic. Whereas if you have a mechanism for collecting data for one scanner and then transferring or adapting that to other scanners, then I think it's reasonable to assume you've got larger data sets that you can play with. But I think that we don't really have a good understanding of these domain adaptation ideas in this context of solving inverse problems for imaging. So in that, I guess that's why it's a hard question to answer. It depends on, exactly what your setup's going to be. And I don't think we really know enough about what these different trade-offs are with distribution drift and forward model drift to really have a good sense of what is or is not feasible yet.
Yeah, that's good. Good comment. So I guess we are going. Our time is up. So thank you again for giving this very interesting talk. And the comments that are online have been very positive. Are you going to be able to share the slides at some point?
So I'm happy to. Just let me know what's best. I can certainly put them on my own webpage, but if you guys have a webpage for the seminar series, I can send you a copy of the slides. And then I also see that Toby asked a question, but I know we're out of time. But Toby, if you just pop me an email, I'd be happy to correspond with you.
Okay, that sounds good. Luca, do we have a website where we?
Yeah, if you can just send us the slides, I can just publish them on our website. Yeah.
Very good. Thank you again.
I'd be happy to.
Thank you.
Thanks a lot, Becca. Great talk.
Thanks again for the invitation. I really appreciate it. Thank you all for coming.
Thank you, everyone.